Thank you very much, Ben, for inviting me. Okay, so I'll first start off with who PanAust is and where the mine is. PanAust is 100% owned by Graham, which is a Chinese company, and the mine that we're talking about is located in Laos. That's owned by a company called Phu Kham, and Phu Kham is owned 90% by PanAust and 10% by the Lao government. So we produce copper concentrate, and the copper concentrate has gold and silver in it, and that's what our sellable product is. So Phu Kham was commissioned in 2008, and the control loop set points were mainly determined by the operators as and how they saw fit. In 2010, the technical director at the time, he decided that we need to change things, and he wanted to automate the plant so that we could improve our throughputs and recoveries. So he put together a team of technical experts, and in 2012, with all seriousness, we started trying to transform this plant. Our strategy that we first looked at what the problem was, and we saw that the operators were sitting down at the bottom and they were just setting all the regulatory loop set points. And we wanted to move them up so that they're actually not adjusting set points. They're just monitoring the operation, and if something goes wrong, they must intervene upon exception. So to achieve that, we had to improve the stability of the regulatory controls, develop some advanced control systems, and then we needed a holistic control which would tie the whole plant into one operating unit. And the operating unit's objectives would be determined by the company's objectives. So that was the idea. The strategy: lift the operator's role from setting individual loops to monitoring and intervening on exception. The expertise lies within the metallurgists. You know, they've done 4 years of studying and so many years out in the field, as opposed to an operator who's been just exposed to a very small spectrum. So we also want to ensure that the plant is always running up against a constraint, so therefore we can get the maximum throughput and recovery. And we wanted to develop solutions that could easily be ported to another plant, so we don't have to redevelop the wheel every time we have the problem. So the tactics were: start at the bottom and stabilize the plant, get the instrumentation working, and apply good first principle loop tuning, which is boring and overlooked. The next step is to improve the operator's situational awareness. So this is very important because the operator needs to know if there's a problem so he can intervene at the right time. So that means the graphics and the alarming has to be designed for the operator. And then we needed to identify what are the best solutions going to be. Because there's so many solutions on the market. We've got these fuzzy expert systems and all other different things. We decided to just go with model-based control. And there's a little bit of model predictive, but it's mainly model-based control. So it's understanding how the plant behaves and then making a control model that will control the plant. And we developed all this in the DCS, and we didn't want to have another black box tied on, which has communication problems between them and all that sort of stuff. The other thing, once we identified a process model and seen, okay, this is how the process behaves, then we wouldn't just go write some control. We'd then look up some papers, just understand, are we sure? Do we really understand why the process is behaving like this? Has other people seen it? So it actually it took a bit of time. It wasn't a couple of weeks that we could just go through this and get it going. Okay, before I go any further, I just want to give a rundown on what the plant looks like. So when I talk about different areas, you guys will know what I'm talking about. So we've got a gyratory crusher at the front end, coarse ore stockpile. and then SAG in 2 ball mills. So a bit of a segregation happens at the 2 ball mills, so they don't behave identical. And then we have everything from ball mill 1 goes to rougher 1, and rougher 2, everything from ball mill 2 goes to rougher 2. Rougher 1 is a blend of both. So they behave slightly differently. The concentrates from the roughers, they go through a regrind circuit before all the fast floating stuff is scalped by the Jameson Cell. And then we have the 3 cleaner banks. We did a bit of modification on the cleaner banks because we found that they couldn't, there was a bit of a bottleneck. So the modifications that we've done around them, and splitting off the first cells, is to address the bottleneck. And finally, the dewatering. Okay, so we started with the instrumentation, and this is often people see this as boring and just run of the mill. However, if your instrumentation doesn't work, nothing's going to work. So what we found was a large number of the valves were incorrectly sized, and the valves were controlling at around 10%. So 10%, most valves have a little bit of hysteresis, 1 or 2%. That's a 20% jump in flow, and we couldn't control the water, and that's the most important thing in the grinding circuit. The other thing we found was the valves were designed, they could meet the pressure, but not the pressure drop across the valve. So there would be a massive amount of cavitation, and eventually the valves would disintegrate. So we had to select some valves that could handle the cavitation and were correctly sized, so they're operating around the 70% mark where valve should be. So although this is very straightforward and obvious, when the guys designed the plant, it wasn't designed like that. So we had all the wrong stuff. The next thing we found was a lot of our flow meters didn't work properly. They were slurry flow meters and not, they were water flow meters and not slurry flow meters. So all the bumping against the electrodes would create noise. So we had to filter out the signal. So we actually couldn't use the flows for actual process control, but we could only use them for mass balancing, and which was a bit unfortunate. And it was very expensive to replace these dirty great flow meters. So that was something we just learned to live with. And finally, ultrasonic level sensors, they're really clever nowadays. So you put them in a tank and you can teach them where all the interferences are. But I found that nobody did that. They just banged them on and set the range, and that's it. So as the level comes down to 40%, suddenly it starts jumping all over the place. But there's a way around it, and we didn't have to deal with all those problems. So there were so many little issues which were very basic, and if you just read the manual on the instrument, you wouldn't have incurred those problems. Right, the next thing I found was the loop tuning. So a lot of the loop tuning was done in the old methods of Ziegler-Nichols, trying to get the loop almost unstable and cracking it one back. Now, you must realize Ziegler-Nichols was derived in the 1930s or 40s, so it's probably not the best way of tuning a loop 80 years later. So the best way to tune a loop, or the way we tune loops at PanAust, is we use hole placement. So you identify the model of how the process behaves, and then you tune the loop accordingly. But what you do is you say, well, what do I want this loop to do? Is it supposed to be a fast loop? Is it a slow loop? Is it a surge arresting? What is its purpose? Once you understand the purpose by speaking to the operations and the metallurgists, then you actually calculate what the numbers should be on the PID block. So there's none of this having somebody twiddling with little numbers and then seeing what the response is. No, you calculate what everything should be, you put it in, and if you've done your calculations right, it's normally right. So that we had to go through all the control loops. Again, nothing sexy or flash. What I found was very disappointing is the functional descriptions of a plant don't describe what the loop's purpose is. It says the level will be controlled by the level sensor, which controls the speed of the pump. But it doesn't indicate the surge arresting, how much time it's got, and that's very important. Have you got 2 minutes, 5 minutes to absorb that surge? And the other thing that I found is no feed forward was used. Now, feed forward control, you get taught at uni, and I think that's the last time people actually do it. The problem with feed forward control, again, there's no Ziegler-Nichols tuning method. You actually have to identify the process, but you have to identify a number of processes, where the disturbance is coming from, where the process that's being impacted, and then you use the combination of the two to calculate the feed forward transfer function. Now, again, we all taught that at uni, so we should be able to do that, but it's not done. And if you get the calculations right, feed forward is so awesome. You have a surge in the grinding circuit, and just boom, the roughness aren't going to be impacted at all. So it's something that's important that has to be done. Okay, so enough whinging about the bottom layer. Now I thought I'll just talk about some small little improvements that we did. And at the crusher, we had the conveyor belt, which is about a 1.2 kilometer long belt, overloading quite often. And then when it overloads, you put excessive stress on the belts and everything else. And what normally happens is a rock will fall off, and that rock will hit the pull wire, and you stop, and then you have to start up on a loaded belt. So we're having a lot of just niggly little issues in the crusher. So we had a look at how can we reduce the overloading, reduce the spillage, and improve it. So the original control was just a very simple PID, the set point, you're controlling to the set point. The problem is you have a feeder over there pouring rocks onto the conveyor, or the short little conveyor. That drops onto the main conveyor, and then the weightometer is over there. So because of the large dead time, you actually can't use a simple PID controller. You have to put in some dead time compensation. So that was the first obvious thing that we put in. Now, dead time compensations were sort of identified by Dr. Smith in 1954, around then, and they still aren't used very often, which is very sad because it's been around for a long time. The next thing we found was whatever signal we gave to that hydraulic feeder, it wasn't necessarily the speed that feeder was going to run at, because the 4-20 just adjusted a little swash plate, and we were just hoping for the best. We did some analyses, and we found that the actual signal, the command signal to this feeder, was quite different to what the feeder was running at, and then we had to ramp it up, and then the feeder would speed up. So to solve that problem, we fitted an encoder onto the feeder, we fed that back, and we put in a little speed control. So now that if we told the feeder to go at this speed, the feeder will actually run at that speed. And we had the dead time compensation, so that improved things tremendously. So before, you can see there was a wide spread of tons on the belts, and anyway, it doesn't. You can see right up there going up to 3,300 tons. That's bad. That's really bad because that's overloading the belts and putting the excess strain on the belts. And in the same, where the motors are really pushing it up at the 400 kilowatts. That's what we want to avoid. So we've increased the throughput from this crusher, and we're running in a much tighter band, and we're not exceeding its limits as often. And what we found was all the pull wire trips and all these funny little horrible issues tended to just go away. So we also did get more throughput through the crusher, but that wasn't the main objective because the crusher wasn't a bottleneck, but it was a nice sort of bonus. So then we had a look at our operator situational awareness. Now the operator is a part of the control system, And without situational awareness, it will take a little bit longer for the operator to work out what's going on, what changes they must make, and sometimes they're going to make the wrong change because they're just not sure exactly what's happening in the plant because for so many reasons. So the biggest problem we found was the HMI colors. They need to be meaningful, and what our system was everything. It looked like a Christmas tree. There's no other way of no nice way of describing our HMI. There were little flashing lights, and it was just chaos. And the alarms need to be very informative to the operator. So when an alarm comes up, it's not just he actually should know what to do, or hey, there's a problem. So this is what our HMI graphics looked like before we started, and you can see it's pretty chaotic. There's green and there were flashing lights, and actually on that day the plant was running well, even though no one can really see if it is working well or not. The 4 alarms which say there's an issue in the float, regrind and auxiliary area, they were just false alarms. So we changed our graphics to green, a very dull green being running and a grey being not running. And if there's a problem, it must be red or yellow or orange for interlocked. And here we can see everything's going well, except one of the valves is out of service. So that's quite easy. And also, it's not like glaring on the operator, so the operator should suffer less fatigue looking at a screen like that. Okay, so our lessons learnt from the HMI alarming is change is always difficult because we had one system and we were moving to another. People were familiar with one set of colors. There was a lot of pushback initially, and then after a while people were saying, hey, no, this is actually better. So, but that didn't happen straight away. It wasn't easy. So converting online graphics online is tricky because you're doing page by page and you don't want to interfere with the operation. So I would say that when you're designing a plant, make sure that your graphics adhere to the ASM guidelines and that your alarming is also adheres to the alarming standards. And these standards are pretty recent. They've only been out for about 4 or 5 years. There used to be the ASA standard, but now there's the IEC and Australian standard for alarming. The take-home message for alarming is an alarm is an audio or visual means of indicating to the operator an equipment malfunction, process deviation, or abnormal condition that requires a response. So if an alarm does not require a response from the operator, it is not an alarm. It shouldn't even be there. It's just maybe if the mechanics want something, they can have some sort of notification system that sends the mechanic a notification, but it's not an alarm. And the biggest problem, once you've started a plant, is to remove all these alarms. So there again, it's so important that in the design phase, all your alarms are specified. The alarm must be this, and the operator must do that when he sees that alarm. Not just, we'll have 4 alarms for every analog signal. Right. Now we get to the fun stuff. That was really my whinge of just getting things done properly. Right. We started at the SAG mill. That was our first bit of advanced control that we started with. And it's a true multivariable system. So we don't want to exceed the SAG, the mill power, the mill rotor current, because it's on a slip recovery unit. The mill weight, the SAG mill noise, the recycled pebble load, and at this plant we've got a constraint of 18 tons of copper going into the plant. We can't exceed that because of the downstream constraints. And we've only got SAG mill feed rates, SAG mill speed, and SAG mill density to control. So we came up with a multivariable model-based control system. And I was asked, how does it actually work? So first I tried to put something together on a PNID, because a lot of people are asking me, when this and if this, like an expert system, but it's not an expert system, it's a model, so I can't say in any one time what's going to happen. I've got a rough idea of it. So I tried to do this and I put together a PID, but I got about halfway and it doesn't cover all the interactions. So all I can say is it's sort of like, as Dirk gently would say, everything's connected, and that's what I'm trying to show. It's a model, everything works together. Then I came up with another idea of trying to explain how it works, and I could say we've got a gain profile, and the controller gain looks at the current throughput of the mill, because the current throughput will give you a good idea of the grindability. It's not the softness or the particle size distribution or the actual ball size or the liner condition. It's a factor of everything. So the current throughput and the rate of change of the SAG mill tells you how much product can get through that mill at the time. And why we change the gain depending on that grindability factor or the amount that can go through. Because if you've got really soft ore, to make the mill weight go up by 10 tons, you're going to have to put a lot more ore in. When you've got really hard ore and it's staying in the mill, if you want to make the mill weight go up by 10 tons, you just put a little bit more ore in. That stuff's not coming out quickly. So we have this gain profile that the mill adheres to. Now, it's actually got a fourth dimension because it also works on speed as well, because the speed is also an indicator of what's happening in the mill. So in some areas on this profile, it actually won't get there, but the speed down in the green area would lift that profile up. So I've sort of made like a bowl in a weird way, that if you drop a marble, which is a mill weight, it will want to run into the middle of the bowl. And that's sort of the best way I've been able to describe how model-based control works. Yeah. And I still think it's a little bit, I don't know if my explanation is good. Anyway, what happened was we increased the throughput of the SAG mill by around 4%. And you can see the power is in a very tight band. The mill weight is in a very tight band. Our product size distribution also improved. What we were finding in manual operation, because we had a very variable ore body, the SAG mill and grinding circuit were a little bit all over the place. We were sending a lot of pebbles into the roughers, and they would actually jam in the dart valves, which caused a problem, which we'll talk about a bit later. But once we implemented this, we stopped sending all crazy particle sizes through to the roughers. So we got a benefit in the roughers as well, but I don't really know what that was, purely from the SAG mill. And we've been working a lot on the SAG mill control. So from about 2012, we've done lots of little refinements, and we've got to the point where the utilization is around 97%. A lot of those refinements were understanding why the operator takes the control out of auto and puts it in manual. There were some disturbances that we just hadn't thought of. So then we had to understand what the disturbance is and then create another little piece to add onto the model so it can cope with it. So things like feeder trips and all those little things, we just combined it in. So the SAG mill just moves as soon as the feeder trips, boom, the speed slows down and it just takes care of itself. And that got the utilization up. The next one was the roughers. And this one, the operators used to walk up and down adjusting the roughers. There's 15 cells, air and level on each cell, and then you've got all the OSA readings that you have to take into consideration, and there's five frother addition points and 5 collector addition points. We had a whole lot of float operators continually walking up and down and adjusting stuff. So that my objective was to automate the whole rougher circuit. And we want to improve, obviously, recovery and have no operator intervention. So that actually was a huge project. It took about nearly 3 years. And what we started off again, we had to repeal the dart valves, we just suffered from pebbles, and then we eventually got everything working, and then we had to say, right, how do we want this thing to control? Because the level and the air and the froth velocity, they all work together and they work on recovery, so it became quite complex. And we had to balance the mass pull between the two roughers. So eventually we came up with a solution, and here is the HMI for that. You can see the operators only set the froth velocity, and then we indicate to them what the froth depth and the airflow is. And the froth velocity is actually determined by the metallurgist, so the operators don't set anything here. In the middle, it looks at the amount of copper coming in, and it determines the mass pull that's required. And then from the mass pull, it determines the frother addition and the levels on the airflow. This gave a huge improvement. So you can see our tail grades in our rougher just dropped down to about 0.08 on average from around 0.12. And it's in a much tighter band. So obviously with our tails dropping, the recovery went up a lot. And we were sending more consistent feed to the regrind and cleaners, so that improved them. Finally, we then started on the cleaners, and first we debottlenecked the cleaners, which was a lot of physical stuff, and then we went on to the Jameson Cell. Now, what I find quite disappointing was Atkinson in 1993 wrote a brilliant paper about how to run a Jameson Cell, and in 2013 we weren't running our Jameson Cell as he recommended, which is quite sad. And then we did all the test work that he pointed out, and we found, yes, everything he says we see in our Jameson Cell. So then we developed a control model based on that, but we found that we were actually missing some instrumentation. Atkinson said you must control the wash-water ratio, but we couldn't, because we didn't know how much pulp we were recovering. So we had to put a flow meter and a density gauge on our concentrate line. So only then could we get the wash-water ratio, and only then could we get this Jameson Cell working properly. So it was a bit disappointing that the instrumentation required to get the Jameson Cell working properly is known, but it wasn't implemented. Then we moved on to the mechanical cleaners, and we had to understand how they were being run, using pH to try reject pyrite, and then increasing collector to try increase the recovery of copper. That doesn't actually work because the pH rejects pyrite and reduces the amount of copper you're going to recover, and then the collector just does the reverse. So you end up just using more reagents for this to get the same result. So we just decided, well, if we have high pyrite, we will try and reject the pyrite just on the kinetics inside the froth. So we're going to treat these cleaners very delicately. So just getting the right amount of air and not pulling as hard as you can in the first cell, but just pulling out a little bit and getting each cell to work all the way through the bank. We found that we would reject more pyrite and get more copper because of the difference in the kinetics of the copper floating and the pyrite floating. So all the things we found is more air results in more water recovery and more entrained gangs, so it's not really the best thing. And I think if you read papers by Cilliers, you'll see a lot of, he's talking about air, not maximum air isn't the best thing, it's the right amount of air is the best thing. So we went about working out which is the right profile, and the profile obviously changes depending on the amount of copper coming into the plant. More copper, you need a bit more air, and less copper, you need a bit less air. So we would move the profiles in cleaner 2 and cleaner 3, depending on how much copper is coming in. The other thing we found is we wanted to control the grades, and I tried using the OSA, and it was really difficult because every now and again the OSA gives us bad reading because the pump just sort of bugs for a short while, or there could be anything. You know, measurement theory always says there will be some dodgy little sample now and again. So I tried putting a first order filter, and what that resulted in was it just delayed the whole the signal so much that I couldn't use it for control, because by the time I wanted to act on that signal, the process would have changed. So I had to find some different form of filtering, and I came up with a stochastic filter, which looks at the probability of error. So if we're running at a certain, and I assume that the probability of error, true reading is if we get exactly the same as the last reading. And the greater the difference, the higher the probability of error. So if you suddenly have a jump, it's probably a bad reading. But if you have another reading up there, then it's probably a good reading. So then I can move the process there quickly. So using that, I can now start using the OSA signals for control purposes in the cleaners. Okay. And then once we had all this information, then I could go about doing the automation. So the aim of the Jameson Cell, we wanted to get a really good quality con of 29%, and then we get the mechanical cleaners to tease out the rest of the copper, and they would only achieve about 20 or 19%. And then the combination would make our 23% con that we were after. Right. Then the cleaners, we found that we would build up recirculating loads, and that became, we'd overload the cleaners. So we're thinking, now how do we get around that? So this is, it's not my bit of work, this is Luke's work, and he came up with a way of determining what the concentrate set point should be on cleaner 1. And then that gives cleaner 2 and cleaner 3 the ability to achieve their objectives. Because if you overload them with too much con, then they don't perform well. And if you give them too little with too high a grade, well then you get a good grade, but you don't get the recovery. So Luke came up with this formula, and it determined what the concentrate grade should be from the cleaner 1 concentrate, determined by our objective that we wanted, and looking at where the Jameson cell is running. And that's just tied together the 3 cleaner backs. So cleaner 2 and 3, we did what we did in some Jameson cell. We implemented some constraint controls and moved the profiles, and that was all determined by metallurgical test work. Right, so now the proof of the pudding of you can see that the copper grade is actually on the Jameson cell, it's come down a little bit, but the recovery has moved up a lot, and we're in a tighter band, so we were actually getting more copper off the Jameson cell. And then we went to the mechanical cleaners, and the mechanical cleaners, well, the copper grade, again, it just moved down a little bit, but the recovery moved up and was in a very tight band. Now if we combine the two together, we find that the actual concentrate grade from the combination moved up, because you didn't have one performing badly and the one performing well. And, you know, those two were sort of seesawing. Now you had them both performing well, and we got an overall improvement in our copper grade, and obviously the copper recovery came up as well. So that was quite, we were quite happy with that. So the journey, if we break it down, and we started with the SAG mill 2012. We just got the feed rate going just to get a bit of stability. 2015 we put in the noise analyzer, and that serves 2 purposes. One, to protect the liners so we don't to get too noisy. The other, we don't want the mill to be too quiet, because what we found on soft ore, the mill would go really quiet. We'd slow it down to try and maintain the mill weight, but we were turning it into a ball mill and there'd be no impact, and we'd build up a large circulating load of pebbles. So we try to keep a little bit of noise in the mill, so we keep busting those pebbles, and we stop building up this recirculating load of pebbles, because the downside of the big recirculating load of pebbles, as soon as the hard ore comes through, you've already got this big load or pebbles, and boom, your SAG mill just lands in trouble. So that was a bit of a win. Okay, the roughers, yeah, it took 3 years. First, just getting the froth analyzers to work to get the right mass that we needed, and then the reagent automation. And then the cleaners, well, took a bit quicker because now we had learned quite a bit from doing the roughers. And finally, we get a utilization of about 95%. So all our automation, we determine what the process does. And I know I've said it many times. So understand the process, model the process, and then determine what's the best way to control it. And make sure that you document everything so you can just port what you've learnt. So we took what we learnt on the SAG mill and we took it to PanAust. We put the same solution in a PanAust. Took about a week, bang, that was running. So the advantages of automation, well, we reduce variation, and that allows us, we reduce the variation so we can bring the process closer to its constraints, so we get better throughput. The understated benefits is the accuracy of the metallurgical test work improves. And this was very noticeable when we were doing our cleaner test work, because we weren't getting surges in the cleaners, and the test work just came out so beautifully. Probably also we got good met techs as well at the site. And then this allows you to improve the model even further. And because your plant isn't going all over the place, you're not exceeding its constraints. So the plant availability and reliability improves as well. So this is sort of a history. Our throughput slowly came up. It came up, then there was a big step when we introduced the second ball mill. And then it sort of stabilized. But you can also see the recovery slowly come up. There was a little bit of a kick when we introduced the IRP project. But it's not a good story. It's actually a bad story, because we lost a lot of recovery for the first 6 years of that plant. That's copper gone. We know it's in the tails dam, but it's essentially gone. We never get it back. So why didn't we start the plant at this higher recoveries and higher throughputs initially? And it would have saved so much more money than this project that we did save. So going back to our little Duncan and I, we put this together. This is our hierarchy of controls. Going back, if you start a new plant, you start off with what are my process objectives, and you work down. Okay, I want it to work like this. Therefore, I'll need that in place. Therefore, I need these controls in place, and therefore I'll need that regulatory control. And these are the instrumentation I need. And now you go and you're building a plant, and it will achieve what you want it to achieve. Also, the functional specification needs to specify what that plant needs to do. So we can't have the control system guys just writing some code on their interpretation. No, the functional spec needs to be a functional spec and tight, so that it tells the guys exactly what to write. And it must, going back to hoppers, and they say we've got so much surge capacity, so that the guys know how to tune those loops for the surge capacity required. Okay, so in conclusion, PanAust used control models developed in-house and to automate our plants. This method has provided robust process automation and very high utilization. The reduction in process variation has increased throughputs and recoveries, and obviously we get more money for that. And the control models can be ported to a new operation, which will reduce the ramp-up time. A new plant must be automated from day one. And when we started PanAust, I said, listen, let's start with the feeder automation. And the guy said, no, we're going to run in manual because we don't trust the automation. So we bogged the feed chute to the SAG mill. And then I said, well, you should have been in order. It wouldn't have happened. I said, no, we wouldn't. Then the second day they bogged the chute again. So then the third day they said, Dirk, please can you put it in order? I said, yeah, sure. So just these silly things that make startup of a plant is so tough. should be avoided if you automate right from day dot. When you commission the plant, commission this automation, not 6 months afterwards. That's it.